So maybe let us start. And I just wanted to show you 3 pictures from this about these B modes, which we discussed yesterday. So B modes are, well, you measure the CMB which is coming to you, you measure its polarization, and you can basically split it into 2 kinds of polarizations, E modes and B modes. And B modes are quite interesting. So if you do this CL power spectrum for the B modes, so CLBB, then what you expect is that this thing is produced due to the gravitational lensing, and you will see a bump here if you have gravitational waves produced during the inflation. Okay, and so this is the prediction. So without gravitational waves, you would see this thing. With gravitational waves, you expect to see that thing. So here is the experiment. It's like Sheldon measuring magnetic monopoles. Okay, so here's the experiment. And really the measurement when okay, so you see what the measurement was. So everybody was very excited. Gravitational waves do exist. So we have first observation of gravitational waves. Moreover, sort of the inflation is confirmed because these gravitational waves were produced during inflation. However, what actually happened is that once you put these results into the results which are, well, if you connect them with what Planck can measure, and so it was actually shown that all this bump, it is there, but it's produced due to the polarized dust in galaxies. So this polarized dust produces magnetic field, if you want, and of course the magnetic field interacts with your electromagnetic radiation coming to you, and so it can affect the polarization of these things. And so all it went away, and so by the way, one of the predictions, because you measured these gravitational waves here, so you could estimate what is the power, total power of these gravitational waves. And there is something which we'll discuss on Friday, which is the ratio of the tensor modes with respect to the ratio of tensor modes with respect to the scalar modes produced by inflation, if you want. And so this ratio is a number, and it was predicted by this experiment because they measured lots of gravitational waves, predicted 0.2. Okay, so now, so we would have lots of gravitational waves, and that this was, a disaster for many, many inflationary models. So basically, it ruled out 99% of inflationary models, most of them coming from string theory. So sort of, you were ruling out the string theory, but as I said, the effect went away, so the string theory is still in game. Okay, so happy times. So today, the ratio is probably expected to be much, much smaller. So it's probably like 0.01. If it's 0.01, then it's likely that we will measure that ratio very soon. If it's smaller, yeah, who knows? Okay. So now, just wanted to show you that. And now, let's go to the calculation. Thank you. And you can read about this much more, so find some papers on arXiv. But interestingly, our director Neil was actually, from the very beginning, he was against this measurement, and he was saying that probably something wrong with the measurement, and he was right. So I think that's great. Yeah.
So when you say this data was invalidated, does it mean that it both went away, or does it mean?
No, so the data are correct. So what they measured is correct, but the interpretation is not. And so what they did is that they inputted other data from some other experiment, showing what is the average distribution of this polarized dust in the galaxies. But actually, the direction they were looking at had more dust than this average thing. So that's why. So they were unlucky in that sense. Yeah. Okay. So now, again, let me just remind you that picture. So what we are trying to do is this big picture. So if this is your co-moving horizon, then you want to predict your CMB power spectrum, and the idea is that your inflation was was driven, let's say, by a scalar field in the simplest case. And the fluctuations of this scalar field, the quantum fluctuations, produce some perturbations. And these perturbations during inflation are stretched out. They freeze here, and then they start oscillating the plasma, and that's why we see the CMB spectrum. So now, what the whole calculation until the end of this course will be about is that we want to find spectrum of these primordial perturbations of primordial perturbations. Okay, and so for that we actually need to quantize. So at this point you have your FRW space if you want, and you have your scalar field, but both of them are perturbed. So you have to solve, basically you have to quantize coupled scalar and gravitational perturbations together. Okay, so needs to quantize coupled scalar plus gravitational perturbations. Okay, so this is quite a complicated task, and so we'll proceed in 3 steps, and we will never do the actual calculations, but it's your homework about that calculation, so you can do it if you want to. So what we will do today is that we will just quantize, well, the simplest possible thing, and that is the harmonic oscillator, as you always do in quantum field theory course. But we will have one more complication which was not present in the standard quantum field theory course, and that is that the frequency of this oscillator can depend on time. So you have time-dependent frequency. So, and you will see that leads to very many new phenomena, basically. So quantization of time-dependent harmonic oscillator. And this is what we will do today. So, of course, we start from the typical Lagrangian. So it's 1/2 q dot square minus 1/2. Now, what is different is that omega can depend on time and q square. So that's your L. Of course, you can find equations of motion, which are q double dot plus omega squared t q equals to 0. So that's your equation of motion. Okay, so first let's find classical solutions, and let's define a scalar product on these classical solutions, and then let's quantize this thing. Okay, as always we do in quantum field theory. So okay, so first let's find a scalar product. So I'll give you the following prescription. So if you have F1 and F2 are solutions of these equations of motion, so F1 and F2 solve equation of motion, then you define a scalar product F1 and F2 as follows. So it's F1 complex conjugate d over dt F2 minus d over dt F1 complex conjugate and F2. Or, you've probably seen this notation, dt and then dtx on both parts, and F2. And this is evaluated at t equal to 0. Okay? So this is your prescription for the scalar product. So maybe it's not the most typical scalar product. If you look at this, what this really is it's actually a symplectic. It's a symplectic product on the phase space. So it's something like a Poisson bracket, right? So you have like, well, you have Q and P and P and Q and so on. So this is actually a symplectic product on phase space. Because it's symplectic, it's antisymmetric. Well, it's non-degenerate, and basically what it is like a Wronskian. Okay? So let's deal with this symplectic product. So now let's assume that I have a solution. So we have one solution of my equation of motion such that FF in the scalar product equals to 1. Then you can show that if you take F star, then F star is an independent solution to the equation of motion as well. So it's linearly independent. Independent solution such that F star scalar product is now -1. And why it's independent is because F and F star is equal to 0. So it's independent with respect to the scalar product. It's orthogonal solution. Okay, so what it means is that, of course, our equation of motion is second-order equation of motion. So I need two integration constants, if you want, to find the full solution. And I can form the solution by taking a linear combination of F and F star, because these are two linear independent solutions. Okay, so this means that you can write Q of t to be, and let's write these constants A and B like AF and F of t, and then AF dagger F star of t. Okay, so this is definitely the most general solution, if you want, of your equation of motion. Of course, using these properties, you can express what AF and AF dagger are, and they are nothing else than the scalar product with the corresponding Q. So you can take F and Q. So where, if you want, AF is scalar product F and Q, and AF dagger is a scalar product of F star and Q. Okay, so very good. So we have the most general solution. So next step you want to do is you want to define the momentum. Okay, so let's define the momentum PT. Well, this is dl over dq dot. Canonical momentum. If you plug it in, it's q dot. So it is AF F dot plus AF dagger F star dot. Okay, so that's your P. Okay, and so now, as always, if you have Q and P and you want to quantize things, you impose canonical commutation relations. Okay, so now to quantize. So far everything is the same, right? So to quantize, promote Q of t and P of t to operators. And impose commutation relations Q of t, P of t equals to I. H bar is 1. Okay, so these are our operators. And of course, you can show that this this relation so when you promote these two operators, the AF and AF dagger become operators, and these are just functions of time in some sense. So if you impose these commutation relations, they induce commutation relations for AF and for AF dagger, right? And so these are just the standard ones. So then we have, so this is equivalent to saying that AF and AF dagger, I hope the sign is right, equals to 1, and the others are equal to 0. AF equals to 0, AF dagger equals to 0. Okay, so this is completely equivalent to that. I knew that I should have written it there. Anyway, so what it means is that we can define, a ladder of states using these creation and annihilation operators, right? So we can define ladder of states. So first you say there is something which is called F vacuum. And you define it to be that it's annihilated by this thing. Then you have n excited state. And F, and that's defined that you create these things many times. So you put creation operators, so it's 1 over n factorial AF dagger acting n times on the vacuum. And you can define F number of operator so NF equals 2. So first you annihilate, and then you create. So first you annihilate your particle, then you put it back, and that counts how many particles you have. So NF acting on this thing, it really gives you N. Okay. So now, this is all quantum field theory you need, right? So I don't know what you were doing in your quantum field theory 1 and 2, but this is all you need. All there is. But, so this is all very nice. But of course, the time depends. So this is true for any omega. But because omega depends on time, things get a little bit more complicated than in standard harmonic oscillator. And the reason for that is that at this point, we have started our discussion with one solution F, and then it gives F star, and then it gives everything here, right? But we could equally start it. We could equally start with this different solution, with a solution G of our equations of motion, right? So let's start now with with solution G. So choosing G instead of F, of course, again require that GG equals to 1. Well, the same thing goes through again, right? So you have that Q of T is now A of G, G plus A of G dagger, G star, and PT is the derivative of that. So A of G, G dot plus A of G dagger, G dot star. Okay, again, you can impose the commutation relations. And it tells you that these are, again, the creation and annihilation operators. And similarly, you can define G vacuum, right? G vacuum, which is annihilated by my G thing. And you can define an excited state in, well, okay, G excited state, G n excited state. Precisely the same definition, but now, well, you have ng, just creating these G operators. Yes?
Just to be clear, this level states that you have there, that's purely like these are eigenschaft of the Hamiltonian.
You'll get to that. You'll get to that. Thank you for that question. Very good. Let's see. Okay. So at this point, it's just, I'm taking any solution here, and then now I'm taking a different solution here, and you have G number operator, and G is AG, dagger. Okay. So now, of course, the problem is that F is not any better than G, right? Why should F be any better than G? So in some sense, you have this complete freedom of choosing your initial solution. But what it corresponds to is that actually it has profound implications. And one of them is that, for example, the number of particles which you observe is an observer-dependent thing. Okay, so I will show you that in a minute. So G not any worse than F stuff. Okay, and so it's one of the implications of this is that notion of particles is ambiguous. So it actually will be the case that only in such very special symmetry cases as you have Minkowski space, you can define particles as representations of some symmetry group which you have underlying. In general, if you have no isometries, if you have no symmetries, you cannot do it this way, right? You can do it perhaps locally, but did you have a question? Yeah, sure. Yeah, so we will not have time isometry, right? But we will have lots of other symmetries. That's true. But in general, if you have curved space, you don't have any symmetry. And so, whatever is the first chapters of Weinberg, how beautiful quantum field theory is, based on representations of whatever, then this all breaks down in curved space. Yes?
All this that you did so far, maybe except for the eigenstate part, will be the same as the frequency was constant. Right?
Exactly. Yeah, I'll just come to that. Yes, I'll show it in a minute. Yeah, it is. Yeah, it's the same question as over there. Yeah, that's exactly correct. Okay. So anyway, so this is just a warning that I can equally do this, and if I don't have symmetries, maybe these are actually different things. The observers will see different things. So in some sense, the reality is actually encoded in your quantum field, not in what a particular observer sees. Okay. So. How to see this? So first of all, I can write my, because G is a solution, and F is a solution, I can write F or G in terms of linear combinations of F and F star, right? So I can definitely write G of T, which is a solution, as a linear combination of F and F star. Okay, I can definitely do this. I'm just expressing one solution in terms of the other solution. Okay, so now these coefficients alpha and beta have their own name and are very important. They are called Bogolyubov coefficients. And they basically are just a transformation from one solution to another solution. Okay, so now what you can show is that since GG is 1, then you have, for example, a relation between this alpha and beta, that alpha star minus beta equals to 1. So now, my original solution Q of t, I expanded originally as A of f of t plus a f dagger f star of t. Now I can write it in terms of g's. So this is equal to a of g, g, and a of g dagger g star. Now plugging in whatever the g is, so through these things, so if I plug here, g is alpha times f plus beta times f star, and the same thing for the star thing, you will find very interesting relation between these creation operators according to f and the creation operators according to g. So from here, you can see that a of g is actually alpha times a of f minus beta star a of f dagger, and a of g dagger is, well, complex conjugate of that, so it's a of so, once you know these Bogoliubov coefficients, you can relate whatever the creation and annihilation operators are on, for one function, and whatever the creation and annihilation operators are for the other function. Okay. So this is all very simple. So now I told you that we can have different number of particles, so let's prove that. So let's start with the simplest possible case. So let's say I'm in F vacuum, right? And so do I see any particles? Do an observer which is associated with G, does he see any particles? Okay. So question is, how many particles G are there in F vacuum? Okay, well, the answer is very simple. So I just have to calculate. So I have the vacuum, and I'm calculating the expectation value of the number of operators in that vacuum. But now, this number of operators here. Okay, so what is this? So 0f. Now, ng is ag dagger ag dagger ag 0f. But I can write ag dagger as this thing and ag as that thing. Okay, so this is 0f. And now I have alpha star af dagger minus beta af, and then alpha af minus beta star af dagger on 0f. Okay. So of course, whenever the annihilation operator meets vacuum, it's just 0. So this term doesn't contribute. And whenever the creation operator meets that vacuum, it doesn't contribute. So this thing is gone. So you have only this term left. So this is equal to, so now you have minus is plus, and then you have beta and beta star. So it's absolute value of beta square. And then you have 0f, af Dagger 0f, which is just beta star, beta square, absolute value. Okay, so you see that even if I am in the AF vacuum, an observer associated with this G would see that many particles. And of course, how many depends on what this Pocolyov coefficient beta is, right? So that's how many particles are there in F vacuum. And so this calculation, well, is the key thing for explaining phenomena like Andrews effect or Hawking radiation or all these things. So once you know this, you can explain all these things. So Andrews effect. Or Hawking radiation. And so on. So basically all miracles which are there in quantum field theory in curved space, you can just explain by this 3-line calculation. Okay, so because this is a cosmology thing, let's not go into black holes and these things, but let's continue what we see actually. Let's learn more about this harmonic oscillator with time-dependent frequency, and let's address your question and your question. Okay. So now the question is, what are the, so usually in quantum field theory, you are choosing eigenstates of the Hamiltonian. So eigenstates of the Hamiltonian are nice states, and you would say the vacuum is something which has the minimum energy, right? So that's something you would expect. The vacuum is something which is almost empty, so zero energy or whatever, the minimum energy. So let's look at the eigenvectors. Eigenvectors of the Hamiltonian. Which of course would be natural states, which you sort of consider. So what is the Hamiltonian? So it's just the Legendre transformation of the Lagrangian. So it's P Q dot minus L. Very good. Our classical mechanics comes in. And we evaluate Q dot as a function of P. Okay, through the definition that P is dl over dq dot. So what it is just, as you expect, 1/2 P square plus 1/2 Q square omega square. So now, because omega depends on time, this, of course, is a function of time. So your energy, if you want, is a function of time. Okay, so what is this? So now I have to plug for P and Q whatever I have these expressions, and let's do it in this F thing. So I'll be plotting Q is AF, F plus AF dagger F star, and P is the same thing. So we have, this is equal to 1/2. So P is AF, F dot plus AF dagger F dot star square. And then plus 1/2 omega square, and Q is the same thing, but now without dots. Okay. So this is what it is. I'm just plugging it in. So now we can collect the terms which have AF, and then you will have terms AF and AF dagger, and then you have AF dagger and AF dagger, and so on. So this is equal to 1/2, no big bracket. So now let's first collect terms AF and AF. So AF and AF is this guy here. So it will have F dot square. It's F dot square. And then I can also get an AF term from here, and it will be 1/2 omega square F square. Okay, so plus omega square f square af af. And then you do the same thing for other terms. So plus f dot square plus omega square f square. The whole thing is star af dagger af dagger. And then you have the third term plus absolute value f dot square plus omega square f square times af dagger plus af dagger af. Okay, just collecting terms like this. So this is our Hamiltonian expressed in terms of these creation and annihilation operators. Hopefully I've done that correctly. So now you are asking which states are the eigenstates of the Hamiltonian. So you are asking, well, so in particular, I can take a vacuum. So is the vacuum, so for the first question, is the vacuum an eigenstates of the Hamiltonian? Okay, so the question is, I act with the Hamiltonian on the vacuum, do I get something like this thing? That's the first thing you may ask. Is the 0f vacuum an eigenstate of this thing? So now, of course, the calculation is very simple because we calculated all these things here. So this thing is annihilated, right? If I act on vacuum, that's annihilated. This thing will survive there. And then this thing is annihilated. And this thing, well, I create an annihilated particle. It will just give me 1. Okay, so if I calculate this thing here, h acting on 0f, it's just, this term survives. So it's 1/2 f dot square plus omega square f square star af dagger acting on 0f. And this term survives, and these things, they just give me 1. So plus f dot, let me write it here, plus f dot square plus omega square f square 1/2 and 0f. So far we are happy. So far we are happy. So now if you look at this term here, well, it's precisely what you would expect. It's precisely, if I call this guy lambda, then this is just a, eigenvalue times the corresponding eigenvector, right? So this term is fine. However, that term, of course, if I act twice this af dagger on my vacuum, I create 2 particles. So I don't have vacuum anymore, right? So in order this to be true, I have to kill this term, right? So I have to set this guy. So need equal to 0. Otherwise, my vacuum is not an eigenstate of my Hamiltonian. Okay. Very good. So let me continue over here. All right, so in order my vacuum to be an eigenstate of the Hamiltonian, I need a condition that that thing is equal to 0, or that f dot is equal to plus minus I omega f, right? So if this is true, and that term is gone, and I have an eigenstate of the Hamiltonian. However, just remind you that, of course, f solves my equation of motion, so f solves that this is true, right? So this is your equation of motion, is still satisfied. Okay, so now what you can do is that you can differentiate this equation. So put a dot in this equation, then I have f double dot equals to plus minus, and I'll have two terms. So I'll have I omega f dot plus minus I omega dot and f. Now I can plug this equation for f dot again. So this thing actually becomes minus omega square f, just using this thing again. I'll have minus I coming from I square and then omega square f. But I require that that equation is satisfied, right? So I have that f double dot is equal to minus omega square f plus minus I omega dot f. But at the same time, this must be true. So the only way how this can be true is that this actually has to vanish. Because of this. Okay? So in other words, omega dot must be 0, so omega must be equal to constant. Okay? So from here, you know that omega dot equals to 0. So only if you have time-independent frequency of your harmonic oscillator, your vacuum is actually an eigenstate of your Hamiltonian. Otherwise, it is not. Okay? So only if omega is a constant, you have preferred set of modes, which are nice modes, which you know from your normal quantum field theory. Okay? So let's look at that. So what happens if you have omega equal to constant? Just remind you whatever you learned, but you will not need it because our omega is not equal to constant. Well, you sort of need it. But anyway, so if omega equal to constant, then this equation is still true, right? F dot is plus minus I omega f. So we can integrate this equation. And let's choose the minus sign here. That's just a convention. So let's choose a minus sign here and integrate it. So the solution is the exponential, right? So solving that equation, you get that f of t is omega t. So this is the solution. You get a constant of integration. This constant of integration is chosen such that f, the scalar product, is equal to 1. Okay. So in this case, we have actually, we have the symmetry. Hamiltonian is time independent. So you have time isometry. The energy is conserved. And you have nice preferred set of modes, which are these modes. Okay. And this is your standard quantum field theory. So in other words, your Q of t is just 1 over 2 omega, and A minus I omega t, and then A dagger, A naught plus omega t, and correspondingly P. And this is something you know from your quantum field theory course. By the way, in this case also H acting on N, these are eigenstates of your Hamiltonian, and they just give you whatever you know, counting how many particles you have. Okay? So if this is true, then your normal quantum field theory is right. Of course, this is the Heisenberg picture of your quantum field theory. Okay? So that would be happy times, right? If you had this, it would be happy times. In general, this is not true. You don't have time symmetry. In particular, in our FRW space, of course, we have this scale factor which depends on time. So we don't have time symmetry. So everything is, expanding. So this will not be true, but let's assume that asymptotically it is true. And if asymptotically this is true, then you can still say something, and you can use whatever you know from normal quantum field theory. Okay, so it's basically something like a standard scattering problem in your QFT, where you say, well, asymptotically I have two particles, which they collide, something weird is happening in the middle, but in the end, asymptotically I get 4 particles out of my interaction. So this is in and out states. You know, and sometimes it happens that you have a picture like this. So this is your time. Goes to plus infinity. Time goes to minus infinity. And, you know, and asymptotically, so this is your omega t, your frequency of the oscillator. And, you know, at t equal to infinity, sometimes it is actually a constant, which let's call that constant omega in. And then something, you know, very weird happens in the middle. And then at t equal to plus infinity, you have omega out. Okay, so let's have this set up. Okay. This is something like a scattering problem in QFT, right? So you know what the particles are here, you know what the particles are here. Something in the middle is you know, strange things are happening, but yeah, so you can talk asymptotically what is going on. So then you can define in modes are simply the solutions of your equation of motion, which asymptotically approach whatever you know from standard quantum field theory at t minus infinity. Okay, so limit t goes to minus infinity of my in mode is just whatever is over there. So it's 1 over square root of t omega in e minus I omega in times t. So this in mode is defined, you know, for all t, but what you require is that at infinitely in the past it was behaving like this guy, and then out mode is the future analog of that. Out mode, so limit t goes to plus infinity now of f out. T is 1 over 2 omega out okay, so that's a definition. What do you mean by in mode and what do you mean by out mode? But as I said, these modes are defined for all the times. So in principle, so there are solutions of your equations of motion for all the times. You just prescribe these boundary conditions or initial or final conditions, right? But because they are both solutions, that means that you can express one in terms of the other, as we did through this Bogoliubov transformation, right? So you can write, f out to be a linear combination of in mode plus f star of in mode, right? So this must be definitely true because they are just two solutions. And I relay them by this Bogoliubov transformation. Okay, so now what we learned all the way there, we can just apply. So by the way, you can define in vacuum. In vacuum is just 0 in, and it's something which is annihilated by the annihilation operators corresponding to this in mode. So this vacuum is actually, but you know, our in mode is very special because it behaves in the infinity like this. So what it means is that in vacuum is actually empty vacuum in the infinite past, right? So empty in the past. So the question is how it looks in the future, right? So, and for that, you just calculate whatever the right mode has the right behavior in the future, and that's the out mode, right? So what you need to calculate is how many particles characterized by out modes are there in this vacuum, right? And that gives you a number of particles in the future. However, in the future, we have n number of particles, which is, so we have the vacuum, 0 in, and now we are calculating n out, 0 in, and we derive that this is just beta square. That was our result from over there, right? So our vacuum will, if it were empty in the past, it's not empty in the future if we have this beta coefficient non-trivial. Okay, so this actually describes particle creation by time-dependent backgrounds. So in particular, if you think about inflation, if you started with the vacuum at the beginning of inflation, now your universe is expanding like crazy. So this omega is changing with time. So you are very likely to end up at the end with something which is non-empty and full of particles. Okay, so you have particle creation due to the cosmological expansion. Okay, so we will calculate that in tomorrow's tutorial. So happy times. So last thing I want to discuss from the theory is the correlation functions. Correlation functions. Maybe there's time to do example, but probably not. So you just define correlation function. You start with the in vacuum, and then you put how many of the field operators you want. So this will be our correlation function. So, of course, 1-point function is equal to what? So Q is a linear combination of A and A dagger. So that's 0. So 1-point function is 0. That's not interesting. But 2-point function is interesting. So now 2-point. And so what it describes is basically it describes the variance in the field of the field in vacuum. Vacuum, or if you want, the size of the fluctuations of the field in vacuum. So what is this equal to? So now I have 0 in QT, 0 in. So now I'm plugging this to be, well, 0 in AF F plus AF dagger F star square 0 in. Okay, so now many terms are equal to 0 again, so you have to multiply these things out. But if you have AF, AF, it will be 0. If you have AF dagger, it will be 0. So the only thing which is non-trivial is AF dagger. So this is equal to 0 in, A in, okay, sorry, in. This is AN dagger plus A dagger in AN times F star in F in, and this is 0 in. So whatever stands there is equal to 1. So this is just equal to F in square. Okay. So we describe the fluctuation, the size of fluctuations of the field, this 2-point function. I have 3 minutes, so maybe I'll just give you the setup, and you will finish it in your tutorial. So in your tutorial, you will precisely study, how many particles are created during the inflation in the expanding universe. But you'll model the inflation as a step function. So basically, you'll say, yeah. So the simplest possible model. And for simplicity, you'll study this in 1 + 1 dimensional space-time. And for massless scalar field. So it will be a very, very simple setup, but okay. So now let's do even simpler one. So consider a particle. So example is a particle creation by the following setup. So you have, this is my t, and at t equal to 0, so you have omega in here, all the way up to t equal to 0, and then you have omega out, which is a different constant after for t bigger than t0. So in other words, omega t is equal to omega in theta function of minus t and omega out theta function of t. Okay. So now, in order to find how many particles are created here, of course, all we need to do is we need to calculate this number here. So in order to calculate this number here, all we need is this beta coefficient, the Bogoliubov coefficient beta. So Bogoliubov coefficient beta relates how my F out is related to F in, right? So first you have to find whatever these F in and F out modes are. So in other words, you need to solve the equation of motion for the harmonic oscillator, provided these initial and final conditions. And then compare these two solutions, find beta, square it, and you get your particle creation out. So for example, I'm saying that if you take F in, okay, so it has to be whatever is over there in the infinite past. But if it's in the infinite past, it is true all the way up to t equal to 0, right? Because nothing is changing there. So that's why this thing must look like 2 omega in squared e minus I omega in t. And this is true for any time which is smaller than 0. Okay, so this is what I require. Now for future, I can have a linear combination of the two frequencies. So the solution will be omega out, the frequency will be omega out, and I can have plus or minus solution. So this will be plus 2 times square root of 2 omega out, and now A e minus omega out t, and then plus another coefficient e minus plus omega out t. Okay, So this is what has to be there. Yes?
Why is this just Fn? Is it like
So remember, Fn is the solution of my equation of motion for all the times. Okay, so it cannot be just a solution for times smaller than 0. It must be also a solution for times bigger than 0. The only thing which you require is that this solution satisfies this initial condition that at t equal to minus infinity, it goes like this. So indeed, at t equal to minus infinity, this thing is 0, and you don't care. So it is equal to that. But you need solution also for t bigger than 0. Okay. So now, of course, what you require is that this mode is continuous across your jump at t equal to 0. So Fn must be continuous, and its derivative must be continuous. Also continuous. So now this gives you two equations, and so you can solve for your coefficients a and b. Right? So you can do it yourself, but here's the answer. So a, so from here, the two equations, a is minus 2 omega in, omega out, square root of that, and then omega in plus omega out, and coefficient b is 1 over 2, okay, b, so that will be plus instead of minus. Everything is the same, but there will be minus here. So it's omega in, which is minus sign, and then plus omega out. Okay, so that's the solution if you impose the continuity of the mode, and if you impose the first derivative is continuous as well. Okay, so similarly, you would find f out, right? So I just impose that at plus t equal to plus infinity, I get whatever I require to get, this thing here. But now it will be for t smaller than 0, then I will have some coefficients c and d, and then combination of e to minus omega e to minus I omega in t, or plus. Okay, so I'll leave that up to you. And then you can relate, so once you have that, so we have f out. If you have that, then you can write f out as this thing. Okay. So try it if you want to, but you will sort of do the same calculation in tutorial. So wait till tomorrow if you want. And so what you'll find from here is that your coefficient beta, if you do it correctly, is omega in minus omega out divided by 2 times omega in, omega out. Okay, which means that the particle creation, so m out in the in state, is just beta square, is just square of that, omega in minus omega out square for omega in, omega out. Okay, so in particular, as a simple sanity check, if omega in equals to omega out, then of course you haven't created anything, right? So that's a simple check. And you can also calculate the fluctuations. So for calculating the fluctuations of the field, you just have to use this formula here, and it's equal to f in square. However, you know what f in is already, so that will give you the fluctuations of the field. Okay, so very good. So this is the first step. We quantize the harmonic oscillator with time-dependent frequency. The next step is to carry this to quantum field theory, and you'll do it tomorrow.